everyone. Thanks for coming. So we're going to take a little trip down south and about 20,000 years in the past and look at ice-ocean interactions off the Sabrina Coast in East Antarctica. But first, we have to figure out what's happening in Antarctica today. So this is a map of ice mass loss around the Antarctic continent. And as you can see, there's really high rates of ice loss in West Antarctica, but we also have pockets of really high ice mass loss in East Antarctica. So I'm focusing on one of these regions for my first chapter, which is the Aurora subglacial basin. And this basin drains 3 to 5 meters of sea level equivalent ice through the Totten Glacier and the Moscow University ice shelves. And so just to imagine what 3 meters of sea level rise would look like in St. Pete, just thinking that this is coming from this basin and not including other sea level rise from Antarctica, we would be underwater and parking on the peninsula would be a lot harder than it is today. So really big issue. And so why are we showing a lot of instability around the Sabrina Coast today? Well, it's really a double whammy. So beneath the ice in the Aurora subglacial basin, there's a network of subglacial lakes and rivers. And models show that when this subglacial network is really active, ice drains to the coast a lot faster. And then once this water reaches the coast, there's relatively warm circumpolar deep water upwelling onto the shelf today, which causes ice shelves to lose some mass. And it caused basal melt of ice shelves, and so ice can stream even faster towards the coast. But there are very few instrumental records of this region, and so we need to go back to geologic records to look at this on a longer term timescale. And so I'm going back to the last glacial maximum, and we usually think of really large northern hemisphere ice sheets, but ice sheets around Antarctica also reach their maximum extent, mostly grounded towards the edge of the continental shelf. And so this figure here, time is going this way. And so we see general warming, and as climate is warming, these ice sheets are retreating. And so I have a Greenland ice core auction isotope curve, and then 2 from Antarctica, one coastal Antarctica really close to the Sabrina Coast, and the one in the East Antarctic interior. And so as you can see, both of these records are showing climate warming, but superimposed on this warming are these millennial scale warm and cool phases in each hemisphere. So looking at Heimer Stadial 1 in this orangey color, it is a cool phase in the northern hemisphere, but actually a warm phase in the southern hemisphere. And then vice versa, during the Antarctic cold reversal, it's cooler in Antarctica, but warmer in the northern hemisphere. And so ice is retreating during the deglaciation. We're seeing rises in sea level, and sometimes, such as during Meltwater Pulse 1A, we can see about 20 meters of sea level in 500 years, which seems like a long time, but that's really quick geologically speaking. But there have been issues kind of pinpointing where this meltwater is coming from. And so I'm asking the question, when did ice along the Sabrina Coast deglaciate? And then why did it deglaciate when it did, and how it possibly contributed to global sea level rise? So I'm using samples from NBP 1402. Here's a map of what we know about the Sabrina Coast shelf. And all this gray area is literally gray area. We don't really know what the shelf looks like there. As you can tell, this region is very icy, and not many studies and expeditions have gone to this area. But based on what we do know, the Sabrina Coast shelf is pretty shallow, but it has this cross-shelf trough that likely goes towards the shelf break. And subsequent studies have shown different pathways that modified circumpolar deep water takes across the shelf towards the glaciers, causing instability. And then eventually we can compare what we're seeing on the shelf to a continental rise, or from a different study suggesting initial ice pullback from the continental shelf edge at about 16.9 thousand years ago. Super quickly, we can also look at what the seafloor looks like to figure out how ice retreated. So if we look on the eastern side, we see these features called grounding zone wedges, and they get deposited as ice has episodic periods of retreat. And then in this trough, we have this really weird feature of stacked, what we think are outwash deposits, and we'll go back to this feature in a little bit. And so this is a very idealized sediment core, just to illustrate what a deglacial sequence looks like. And so if ice is grounded near a site, we get a lot of terrigenous material being deposited along rocks, quartz, grain material. And as the glacier pulls back, we start to see more of a marine influence. And so we see this type of progression. And on the right are just some pictures of CT scans from the cores illustrating that it looks really cool. And so once we figure out what is deposited, kind of what the glacial environment is like, we then have to figure out when this was all deposited. So typically we would go in and date any carbonates in the core, but there are some issues with this. One, there are no carbonates in my cores. And two, they're not, if they are there, they're not the exact horizons that we want to date. So then we go in and use bulk sediment dates. And then the issue with bulk sediment dates is that glaciers churn up a bunch of different materials. So you get a bunch of different carbon pools in your sample. And so I'm using a technique called ramp pyrolysis in Brad's lab to separate all these different pools of carbon based on their thermochemical stability. And so ideally, the youngest carbon, which is our depositional age, comes off in the first slit. And so that's what we date for our radiocarbon ages. And then to look at why ice retreated when it did, I'm reconstructing paleo sea surface temperatures using a lipid biomarker called TEX86. And here's the calibration curve we use with core top TEX86 values and measured ocean temperatures. And so we use this correlation curve to reconstruct temperatures into the past. And then we can compare our temperatures to different paleo-environment reconstructions, such as from diatom assemblages. So are we seeing more ice? Are we seeing offshore influence? They can really help us tie the picture together. And then we can compare what we're seeing in the ocean to atmospheric forcing in ice cores. And just to illustrate, I'm going to show a bunch of sediment logs. So this is the entire core. And then for each core, I'm highlighting just the deglacial section in yellow. So this is the deglacial section for JPC 57 blown up. Here's the core photo. Here's the CT scan and all the radiocarbon dates I obtained. And I highlight the age we're using as the deglacial age with the arrow. And so for the shallow middle shelf for JPC 57, we see deglaciation at about 18.2 thousand years ago. And at JPC 27, we see deglaciation at about 16.2 thousand years ago. And then going into the trough, we look at KC9, which is outside of this outwash deposit. We see deglaciation at about 16.4 thousand years ago. And JGC 39, which is poured through this lobe stack, and this picture does a really good job showing just how stacked these units are. And so this isn't really technically a deglacial age, but we're using this age to figure out, okay, how long did it take for this unit to be deposited? And so this deposition ended about 13.9 thousand years ago. And then finally, we have JPC 43, which is our most ice proximal shelf site, which is in this bathymetric channel. We see deglaciation at about 15.6 thousand years ago. So putting this all together, we first see deglaciation on the shallow middle shelf at about 18.2 thousand years ago. And then we see pretty rapid succession from there at deglaciation at JPC 27, KC9, and JPC 43. And then JGC 39 is doing its own little thing in the trough. We plot all of this on a timeline. First, you see, wow, they all kind of cluster around 16,000 years ago. And then you look at it again, you say, wow, the error on these ages are really large. And that is true. And that's just kind of an inherent issue we have to accept using ramp pyrox. So we get a more accurate date, but the precision is blown up a little bit. And then also, as you go further back in geologic time, dating these really low organic, basically organic pore sediments, the error inherently blows up. So this is kind of something we just have to accept. But if we look at the deglacial age of when ice first pulled back from the continental rise, we see that these ages all kind of line up and they kind of agree with each other, which is great, but also concerning because we see very rapid retreat across the entire shelf at the same time. And so looking into the mechanisms, I just pulled out a few of the cores. I'm not going to go through all of them. But here is the deglacial section only for JPC 27. And then I have plotted the total diatom abundance and then two different diatom species, F. kerguelensis, which is an indicator of offshore influence, and then T. antarctica, which is an indicator for platelet ice formation. And so looking at these two species, we can look at are waters coming onto the shelf versus is ice forming here. And then finally, we have the TEX86 sea surface temperatures. So going from bottom up, during the deglacial sequence and slightly preceding deglaciation, we see relatively warm temperatures. So we're seeing this as an indicator that warm waters are coming onto the shelf. And then after ice retreats a little bit, we get this locally restricted basin type sedimentation. So we get these laminated diatom muds and oozes. And these get caused by meltwater coming from the glacier. They're super rich in nutrients, so they fuel these blooms. And then we get this bioturbated diatom mud unit. And in this unit, we see an increase in the T Antarctica, suggesting that there is some ice readvance at this time. And then looking in the trough, we see very similar things at KC9. And so we're assuming that ice deglaciated across the entire trough at about 16.4 thousand years ago using the KC9 age. And again, we see warm temperatures during the deglacial, and then we see this increase in ice cover or ice formation after deglaciation. And so using the age differences between KC9, since we think ice retreated, and JGC39, which records the latest age that these outwash deposits were being deposited, we see that they were mainly deposited in about 2,500 years, between 16.4 and 13.9 thousand years ago. And that's really interesting because that timing lines up to when we're seeing meltwater at our shallow middle shelf sites. And so we think that this outwash deposit was likely deposited by meltwater coming from the glacier. So if we put this into a global climate contact, all of the ages cluster during this warm phase in the southern hemisphere, which is Heinrich Stadial 1. And so the warm sea surface temperatures we're seeing support hypotheses that this was a warm period in Antarctica. And actually, we think that this warmth led to deglaciation of the Sabrina Coast. And then finally, we see lots of evidence of meltwater, suggesting that this is a very meltwater-rich deglaciation contributing to global sea level rise. And the timing is a little suspicious, and we have to tease this out more, but all this meltwater is possibly contributing to meltwater pulse 1A.